At PanEuro, we recognize what others won't say out loud. The AI and quantum computing revolution has fundamentally rewritten the energy equation. The numbers are staggering. Data center consumption could hit 945 terawatt-hours annually by 2030, more than Japan generates today. Meanwhile, renewable deployment faces hard limits: grid stability challenges, critical mineral shortages, and physical infrastructure constraints. The 2050 net zero ambition remains important, but pursuing it through renewables alone while scaling AI infrastructure isn't just difficult, it's impossible. The math doesn't work. The physics doesn't work. The timeline doesn't work. An honest energy strategy requires an uncomfortable admission. Natural gas isn't a fallback option during this transition, it's the foundation. Lower carbon than alternatives, backed by established infrastructure, it's the only fuel that can simultaneously power the computational revolution and stabilize grids as we build toward a renewable future. We can have bold climate goals, or we can have reality. The question is whether we're brave enough to choose both. Achieving both AI infrastructure scaling and aggressive decarbonization through renewables alone is scientifically and financially unrealistic. An honest energy strategy must recognize that natural gas, as a lower carbon transition fuel with established infrastructure, will be essential to powering the computational revolution while simultaneously supporting grid stability during the multi-decade-long energy transition ahead. The artificial intelligence revolution has created an energy demand curve that defies historical precedent. Unlike previous technological transitions that unfolded over decades, AI infrastructure growth is accelerating on a timeline measured in years. Current data centers supporting generative AI and machine learning consume approximately 130 terawatt-hours annually as of 2025. Yet research from Goldman Sachs and other modeling organizations projects a 165% increase in data center power demand by 2030, a trajectory that would place total electricity consumption in the range of 846 terawatt-hours annually. Projected data center electricity demand showing exponential growth driven by AI, illustrating capacity constraints and the necessity of diverse energy sources, including natural gas, during the global transition. The climate policy advocates for rapid scaling of renewable energy to achieve net zero 2050 objectives. Yet the engineering and grid data reveals fundamental constraints that policy discussions often understate. Grid intermittency and stability challenges are not peripheral issues, they are systemic architectural problems. Worldwide electrical grids evolved over a century to balance centralized baseload generation with distributed demand. However, renewable energy is at odds with this infrastructure. Production is intermittently distributed while demand concentration increases from data centers requiring constant computational throughput. As data center demand grows by at least 165% over the next 5 to 6 years, peak demand periods will generate unprecedented loads precisely when renewable generation is offline or insufficient. Critical mineral supply chains present an additional bottleneck that the renewable energy acceleration narrative inadequately addresses. The shift to renewable energy creates acute dependencies on lithium, cobalt, nickel, and rare earth elements, concentrated in specific geographies with complex supply chain vulnerabilities. The Global South controls roughly 70% of lithium production, 60% of cobalt reserves, and holds near monopolies on rare earth processing. Supply chain disruptions or from mining bottlenecks translate directly into delayed renewable deployment. McKinsey and the Energy Transitions Commission estimate that the net zero energy transition requires $275 trillion in capital spending through 2050, equivalent to $9.2 trillion annually. or a $3.5 trillion annual increase above current investment levels. This represents capital reallocation at a scale without historical precedent. Renewable deployment will necessarily proceed at constrained pace. The physics and engineering of scaling wind and solar cannot be accelerated beyond certain physical limits, regardless of capital commitment. Let me please make this essential point. We acknowledge that climate change is real and serious. But acknowledging this does not justify adopting energy policies that are financially unsustainable or technically infeasible. Now, let's consider natural gas. Natural gas occupies a crucial but often dismissed position in any realistic energy transition. The fuel possesses characteristics that renewables cannot replicate across the required infrastructure timescale. For example, in terms of energy density and storage, natural gas contains approximately 36.5 megajoules per cubic meter, enabling compact storage and transport that is fundamentally superior to electrochemical storage technology at current development stages. For data centers requiring sustained 125 kilowatts per cabinet, with cooling demands adding another 40% to total electricity consumption, the requirement for reliable 24/7 power at scale has no demonstrated renewable-only solution. Perhaps most critical, natural gas generation responds in minutes, providing the frequency regulation and voltage stability that keeps grids stable as renewable penetration grows. It doesn't just fill gaps, it enables the renewable transition itself. Energy transitions reshape geopolitical power structures. The shift from coal to oil in the early 20th century concentrated geopolitical power in petrostates. A renewable energy transition creates different vulnerabilities, dependencies on specific minerals concentrated in specific nations, with supply chains vulnerable to disruption. China controls approximately 70% of global battery processing capacity, a concentration more acute than OPEC's historical oil leverage. Energy security will require reformulation around reliable access to renewable energy, secure supply chains for critical minerals, and resilient power infrastructure that functions during geopolitical disruption. Natural gas, produced across diverse geographies with relatively decentralized supply chains compared to renewable minerals, will enhance energy security during the transition period by reducing dependency concentration. The economic calculus is equally stark. Net zero transition spending requires multiple trillions annually above current investment levels by each developed nation for the next 25 to 30 years should exhortation and policy declarations be put before common sense and reality. The computational revolution isn't just happening alongside the energy transition, it could fundamentally transform it. AI has the potential to accelerate renewable energy deployment and optimize how our electrical grids operate. Take cooling efficiency in data centers, for instance. Google's work with DeepMind has already shown how AI-driven algorithms can significantly reduce cooling energy needs. Beyond that, AI can speed up materials science research, helping us develop better batteries and more efficient solar panels. To unlock these benefits, we need to get the sequencing right. We can't use AI to optimize renewable deployment if we can't build the AI infrastructure in the first place due to energy constraints. The solution: build the computational infrastructure first using the most reliable energy sources available, and yes, absolutely including natural gas. Then deploy that capacity to solve the complex optimization challenges of the renewable transition. Quantum computing may eventually offer exponential computational gains with minimal energy increases, but it's not production ready for grid management yet. We'll need classical AI systems running in parallel with quantum development well into the 2030s and beyond. The inescapable truth is this: something must yield. We face a fundamental choice. Either we extend our decarbonization horizon to 2080, abandoning the 2050 target while still pursuing renewables with urgency, or we acknowledge an unpopular reality: natural gas isn't optional. It's the foundation upon which we'll build the AI infrastructure that ultimately unlocks our energy future. The second path isn't just realistic, it's the only path forward. Nations that embrace pragmatic energy policy, that treat natural gas as the bridge while simultaneously driving renewable and quantum computing innovation, will do more than attract capital and secure reliable power. They will achieve what their idealistic counterparts cannot: actual decarbonization. The reality is we can't pursue unlimited AI deployment while hitting 2050 net zero with renewables alone. Honest climate advocacy requires honest energy policy, and that means acknowledging natural gas as an essential bridge infrastructure for the decades ahead. The sequencing matters. Build the computational infrastructure using the most reliable energy sources available, including natural gas, and then use that computational capacity to solve the increasingly complex optimization problems of the renewable energy transition. For more information, please look up paneuro.co.uk/energy-transition. Thank you for listening, and bye for now.